To welcome you to the Summer School on Quantum Information and Quantum Technology 2022, organized by ISR Kolkata. And yeah, let me begin by thanking the organizers for having such a wonderful workshop conference, which I think is extremely helpful for young students and researchers. And also let me thank the speakers who are going to spare some time to give us some nice insight about their research and what they've been working on. So it's my pleasure to invite Namrata Shukla today, who's been my former colleague and who's currently a faculty and an assistant professor at Banaras Hindu University in the physics department. Just to give you a very quick background, Namrata did her PhD from University of Allahabad in the famous quantum optics group, followed by postdoctoral fellowships at HRI Allahabad, and then IQST in Calgary in Canada, followed by a brief period at Max Planck Institute in Erlangen in Germany before she joined as a faculty at BHU. So today she's going to talk about PT-symmetric systems and how you can define uncertainty relations there. And with that, I'll hand it over to Namrata. Please take over, and thanks.
Thank you. Thank you so much, Hemandri. It was really wonderful to see you after such a long time, and it is a privilege that you are introducing me on this platform. And before I begin, I would like to thank the organizers of QIQT 2022, especially Professor Panigrahi, because this has been such a wonderful event for the last 2 years. I also followed all the lectures last year. And this is like, I just discussed with my friends that this has been such a good platform to almost get all the names from quantum information science on one platform, at one place, and all of them have talked about their work. And this, I'm very, very sure, has been very useful for young students, as Himadri pointed out very correctly. So yeah, it's a privilege to be here. Thank you so much for inviting me to speak in this conference. And today I would be talking about uncertainty relations. So to just give a brief overview, in fact, I did my PhD in quantum optics, but then I switched to quantum information science. And in fact, I was doing more of the foundational work at HRI, which is where this work on, in fact, my works on uncertainty relations began. And this is one of those, so I still continue to do that, explore in that particular area. Okay. Okay, I thought I should be able to change the slides with this, but apparently, okay. I'm sorry about this. Okay, so this is BHU, where I do work, the very ancient physics department of BHU. And so in my talk, which is about the uncertainty relation for non-Hermitian systems, in particular PT-symmetric non-Hermitian systems, I will be covering these 7 aspects. So I will give you some background, and then I will talk about what was my motivation to do this work. I will take the very simple example of 2x2 systems, and then I will try to generalize it to n×n systems, any arbitrary dimension. We'll talk about how it can be useful generally for PT-symmetric systems, and then I will summarize. So this is the idea. This work, the archive number is given, has been done in collaboration with Dr. Ranjan Modak from IIT Tirupati, and one of our faculties here at BHU called Professor Bhavani Prasad Mandal. So this work, I would like to mention, actually came out from a talk that I was giving at BHU to basically introduce myself to other faculty members or the department, because we have got a huge department of about 50 people. So it's really important that you can interact with them on a platform by giving a talk or something, because it is quite difficult to do one-to-one interaction with 50 people over here. Okay, so just to have a little colorful start, I thought I will talk about, in one slide, I'll talk about quantum mechanics. So I kept this slide as quantum balls and tall walls. So I think you already have an idea. What I'm going to talk about here in this slide is that if you had a classical wall, and let's say you had a potential barrier or a tall wall, which I call, so you will not be able to, throw the classical ball across this wall. But if you had a quantum ball, you have a certain tiny probability that you can throw it through this tall wall, and it will land in the area that is classically forbidden. It's a region that is classically forbidden. And that is basically quantum tunneling that I'm talking about. Okay, so this happens mathematically because when you write down the Schrodinger's equation, you will see that there is a non-trivial solution that does exist in the region that is forbidden classically. So this is, I can simply put quantum mechanics in this one slide to just introduce, of course, not to cover it all. And then one of the very important tenets of quantum mechanics is uncertainty relation. The idea of quantum mechanics is based on the uncertainty principle. And to understand that, maybe we can take a look at this picture. So we all are very familiar with the Heisenberg's uncertainty principle that we do in the textbook, and that reads delta x, delta p, the product of delta x and delta p should be greater than or equal to this h cross over 2. Okay, so if we want to really understand uncertainty principle, there can be various ways to look at it. One of them is here, like if I do look at this wavefront, I can see that the uncertainty in position delta x is very high, but then this wavefront is probably constituted of one wavelength. It has only one wavelength, so delta p is going to be very low. Now in the second image, the second part of the picture, we can see that if we have this particular wave packet, we can see that we can reduce the delta x, but then delta p will be very high because this particular wave packet is constituted of several waves, basically. Then in the last case, you can see that you can really reduce the delta x drastically, but then delta p is going to be very high. So it is basically a trade-off between the delta x and delta p, and you know what the deltas denote here. So those in layman's terms, they talk about the fluctuations when you're trying to measure position and momentum. So this was original Heisenberg's uncertainty principle, and this inequality basically talks about mathematical formulation of this principle as it was thought of at that particular time. And then later on, there has been quite a bit of debate, especially in the last 2 decades, about what is uncertainty principle and whether its mathematical formulation that we look at is what it was thought at the time when Heisenberg actually gave it or wrote it down in his originally German paper. So before I move ahead, I'm not going to get into those debates on uncertainty principle or uncertainty relation, so to say, because I remember Dr. Pankaj Agarwal from IOP spoke on this topic yesterday quite in detail. But maybe to have, for students especially, to understand uncertainty relation a little more, in an elaborate manner, you can think of electron microscope. So you're trying to precisely measure the position of the electron. What you can do is you can basically illuminate it with light, and your precision will basically be of the order of the wavelength of the light that you are using. So what you could do to precisely measure it is use very low wavelengths. So maybe gamma rays you can use. But when you do that, you cannot simply ignore the Compton effect, and then your electron is going to suffer a recoil, and hence there will be a disturbance in the measurement of the momentum. So that is another way to look at the uncertainty relation. So it is basically talking about the trade-off in the measurement. Now, just to have this complete in the sense that I would like to talk about, because I talked about uncertainty relation and used the term measurement, I should go through the basic ideas of quantum mechanics and its metrics formulation. So I'm sure all of you already know this because there has been quite a lot of talks on this, but still I'll just go through it briefly. So a quantum system in its in the matrix mechanics formulation of quantum mechanics, a quantum system is basically described by a quantum state which contains the probabilities of possible observables. What I mean by that is that when you do the measurement, you can have the probability distribution and on these states. And what are observables? So basically observables are Hermitian operators. They can be written down as Hermitian matrices in an appropriate linear vector space. And the eigenstates of these observables will simply be the column vectors in that particular vector space. When you do measurement, you try to measure a quantity on, let's say, or you have an observable, you try to do the measurement. What happens to the system is the measurement result will be the eigenvalue and one of the eigenvalues, and the state of the system or the system will reduce to, to a state that is the corresponding eigenvector. Okay, so now when you are doing the measurement, obviously it is not a good idea to do the measurement, at different times or consecutive measurements on different, states, but it is rather a better idea to have a large number of identical copies and then do the measurement at once. And when you do such a measurement, you can have the average value of an observable defined by this relation. This is all very familiar to all of us. So this is generally about the how you deal with quantum mechanics and or quantum mechanical systems in the matrix mechanics formulation. Okay. So now I will come back to the uncertainty principle because this is actually the topic. And as I already told you, uncertainty principle is basically a statement about fundamental limit to the precision with which two complementary variables can be known. So now, for example, we are talking only about two variables, but now it has been generalized to several variables and, even not just product. It is not limited to product of the fluctuations. It can even be sum. So there has been a lot of progress, but I'm not going to get into that direction. Our uncertainty principle, which is in the textbook form we are writing down here, talks about the fundamental limit to the precision in measuring any two complementary observables. It can also be called, they can also be called incompatible observables. Basically, they are non-commuting observables that we are trying to look at, okay? So after Heisenberg gave this delta x, delta p inequality, Robertson was the one who basically generalized this relation for any two general observables A and B, because this can be position momentum, this can be energy time, this can be any of your two favorite angular momentum operators from quantum mechanics, and they all will close on to an uncertainty relation. Okay, so the generalization reads like this: delta A squared, delta B squared will have a limit. The product of these two will have a limit, or it is bounded by this commutation, this factor, which includes the commutator of A and B. Okay, where again, delta A squared is simply quantum fluctuation or variance, as you call it, and this is given by this equation. So this is, I think, familiar to all of you. Okay, so now what we have to do here in order to go ahead is to make life easy. Let's define a quantity called eta, that is the ratio of left-hand side and right-hand side, because in order to see where is this inequality, this uncertainty relation violated or not, maybe it's a very good idea to just define the ratio of the two sides, left-hand side and right-hand side. So whenever we can see that how eta is basically scaling and when it is violating the uncertainty relation and when it is not. So this is very important. It is simply the ratio of the left-hand side and right-hand side of the uncertainty relation that we are looking at any given time. Okay. So now I will get back again to the standard quantum mechanics. Why? Because I'm going to be talking about PT-symmetric non-Hermitian quantum mechanics, so or such systems. So it is a better idea to remind you that in the standard quantum mechanics, our Hamiltonian that describes the system is always Hermitian. Okay, and what it does, it basically guarantees the real energy spectrum and a unitary evolution of the system. Okay, then what are the observables? The observables are basically Hermitian operators in the usual quantum mechanics or standard quantum mechanics, with the measurement result, as I already told you, as one of its real eigenvalues, and they are called observables. So they're just Hermitian operators. Okay, why I'm talking about all this is when we looked at the uncertainty relation, there are two things that do matter here. Number one is observables, and number two is the states. So these are the two things that are very important. Okay, so when I say Hamiltonian, it has something to do with the state, in the sense that if you make use of evolution, or even if you don't make use of the evolution, you can look at the eigenstates of this Hamiltonian, and that would serve for the state. And the other one is observables. Okay, so these two are Hermitian in the standard quantum mechanics. Now, recently, there has been a proposal for a new, new way to look at quantum mechanics, and that is called PT-symmetric quantum mechanics. So basically what happens here in this is that you had a Hermitian Hamiltonian, but now you don't want to have a Hermitian Hamiltonian. You want to have a non-Hermitian Hamiltonian, for example. Okay, so this hermiticity condition on the Hamiltonian can be replaced. And how do you replace it? You replace it by using a special type of symmetry that is called PT-symmetry. And P here stands for parity, and T stands for time reversal. So if you do this operation, PT-symmetry, it is also called space-time reflection symmetry. So you make use of this in order to remove the hermiticity of the Hamiltonian. And now, if you have this, if your Hamiltonian follows this, it is PT invariant, then you can have a non-Hermitian Hamiltonian, basically. And now, how does it work? So a system that is described by a PT invariant non-Hermitian Hamiltonian can be divided into two phases, or it can have a transition from one phase to the other. One is called PT symmetric phase, and the other one is called PT broken phase. So what are these two things, basically? So what happens in the, so basically I will, as I go ahead, it will be clearer to you that we can have a parameter in the Hamiltonian that can basically help it to transit from one to the other. Okay, but what typically happens is that in the PT symmetric region, your eigenvalues are real. So the spectrum is real, and in the PT broken phase, it can be complex as well. The other thing is, in the PT symmetric region, your eigenstates are going to be the eigenstates of the PT operator, but not in the PT broken phase. So these are simply the, if you want to differentiate the two. But for the purpose of mathematically writing it, you can simply have a parameter that scales, and you can see that the system transits from the symmetric to the broken phase. And when I talk about the transition, there must be a point which is basically distinguishing these two regions, and that is called exceptional point that I would be calling EP, and that differentiates the two phases for the particular Hamiltonian. Now, what is very important if we want to take a non-Hermitian PT-symmetric Hamiltonian to describe the system, our quantum system, our Hilbert space that we are using must be equipped with an appropriate inner product. Okay, so because unless you have the inner product, you cannot define any of the quantities that you are going to be using in your uncertainty relation, basically. Okay, so there has been various candidates for inner product for such systems, which are described by PT-symmetric non-Hermitian Hamiltonian, and some of them are PT inner product, CPT inner product, and they have different, different pros and cons, so to say. But The most suitable inner product candidate right now probably is a metric-based inner product, and we call it, or not we call it, it was actually introduced in this paper in 2021. And this is basically a metric-based inner product, which makes the eigenvectors of the Hamiltonian orthonormal. And the best thing about this, so it fits in very well for all the purposes in quantum mechanics. But the best part of this inner product is that it can be extended to the broken phase, unlike the inner products that were defined earlier, which were only valid in the symmetric phase. How is it defined? So it basically uses the geometry of the quantum states by means of a connection compatible positive definite metric operator G. So you can look at it just as a matrix. Okay. And this can be given by this particular equation. Okay. Where Li, so this is what is the definition of G. And Li is nothing but the ith left eigenvector of the Hamiltonian. So if you have a Hamiltonian, you can define G. Now this G is Hermitian, and its dual vector will be defined in this fashion. Okay, so it is the, when I say Li is the ith left eigenvector, it always acts from the left basically. So using this definition, you can see that when you write the dual vector, the G will be simply, stitched here, and the inner product will look like this. Okay, so the inner product of the two states at, let's say, in this framework of inner product, which is G-metric inner product, will look something like this. So you can see that if you have this G is equal to identity, you simply reduce to the Dirac inner product. Okay, so this is very simple in the sense that it can just be sandwiched with your operator if you wanted to get an expectation value. Okay, so now I come to the actual motivation after the background. I hope it was clear. The motivation to do this work or to derive, the uncertainty relations for non-Hermitian systems is that, the first thing one wonders is that if we have such systems existing, then what are the uncertainty relations for these systems? The systems that can be described by non-Hermitian Hamiltonians. The other thing, let's suppose that we have such an uncertainty relation, then you start to wonder what happens to the observables. Do they still remain Hermitian operators like the usual quantum mechanics or not? And the third thing is that what happens to, the system size? Let's say that we can do something for a 2x2 system or a small size system, but how does it work for a large scale system or large size system? Let's say, for example, I have an arbitrary finite dimensional system, and how does these uncertainty relation work for that? So these were the very basic questions that we were wondering, because nobody had looked at uncertainty relations for this kind of non-Hermitian systems. So as it turns out, the answers are simple to describe because again, this is foundational stuff. So you just do your thing with using this inner product candidate that we are using, and we get to some very neat and clear results. So the first thing that we get basically is that there is something called good observables. So we had these observables in the Hermitian systems if we had our usual quantum mechanics. Now we will have to probably resort to a more general class of these operators, and that we call good observables. Okay, and we can see that, so this G is of course our metric, G that I defined in the inner product, and O is a general observable that we are looking at. Okay, so when we are looking at the non-Hermitian systems, this particular condition, O dagger G is equal to GO, or this special kind of commutation relation, is what needs to be followed in order to have a good observable. And when I say good observable, what I mean that the observables that will not violate the uncertainty relations, basically, okay? So these have to be the observables in the non-Hermitian systems. Now you can see that this condition is very simple in the sense that if you have your G is equal to identity, it simply reduces to O dagger is equal to O, which is your condition on the observable to the Hermitian operator, basically in the usual quantum mechanics, right? The other thing is that if you take the hermiticity into account, right, yeah, so I don't probably need to mention that point over here, but yes, so it reduces neatly to the hermiticity condition in the usual quantum mechanics, okay? Now, what is this good observable class? So earlier we were saying that the good observables in the Hermitian systems or for the Hermitian systems can be only Hermitian operators. But now we have come to the point where we can claim that actually they can be Hermitian or non-Hermitian, both. Apparently, there always exists a similarity transformation, which will go like this, that can map the non-Hermitian good observable to a Hermitian operator across the spectrum. So when I say across the spectrum, I mean in both PT-symmetric and the PT-broken phase, okay? So this is one thing. Now that we have the uncertainty relation, we have the good observables, we can always construct the uncertainty relation. And what do we need to construct the uncertainty relation for non-Hermitian PT-symmetric systems is simply write down our fluctuations using the inner product, which is G inner product. So in the framework of G inner product. And the uncertainty relation typically looks like this. So you see that these fluctuations in the observables A and B have the subscript G. And what it means is in the expression, this G is basically sandwiched or stitched with the A square term, which you are usually having in the Dirac inner product framework. Okay, so this is how the uncertainty relation looks like for such non-Hermitian systems, PT-symmetric non-Hermitian systems. And now we want to see how these things work together, or like how the uncertainty relation basically gets followed for these good observables, and how we can see the violation of these, and then finally go to the arbitrary dimensional system. So we will start with an example. But just to mention, A and B being good observable here guarantees, I think I have already mentioned this, but it guarantees that the uncertainty relation B holds in both the phases. So in the PT-symmetric as well as in the PT-broken phase. Okay, so now again, if you remember, I defined an eta for the usual Robertson uncertainty relation, and now I define eta G. So this is everything similar, the ratio of left hand side and right hand side with a subscript G, because now we are in the G inner product formalism. Okay, so we have the eta G. Okay, so now to the real stuff where we can see the examples actually. And Hemandri, how much time do I have?
I think a little less than half an hour.
Okay.
Or maybe we have to keep some time for questions. So maybe it would be good if you can wrap up in 20 minutes and have 5 minutes for questions.
Sure, I'm good. Yeah. So for the 2x2 non-Hermitian systems, the very cute and simple example of a PT invariant Hamiltonian is this. And let's say that its eigenvectors are E1 and E2. So this Hamiltonian, as I mentioned earlier, can be divided into two phases. So where your gamma is less than or less than 1, it will be in the PT-symmetric phase, and for greater than 1, it will be PT-broken phase. And of course, your gamma is equal to 1 will be the transition point or exceptional point, EP, for this Hamiltonian. We'll look at, so this is the Hamiltonian that we take. And we are looking at the generic state because we need the state in order to verify the uncertainty relation or check them. So the generic state that we are looking at is a superposition of the E1 and E2, a general superposition of these two. We have the parameters P and theta that will help us look at different states. Okay, now I would just like to mention here that the minimum uncertainty states are the states that saturate the uncertainty relations, any uncertainty relation. And when I say saturate, the inequality turns into the equality. So both sides become basically equal. And now also, of course, we have the Hamiltonian, and we talked about the PT-symmetric phase and PT-broken phase, but also we can talk about a state being PT-symmetric state or PT-broken state. So it is simply called a PT-symmetric state if it respects the PT-symmetry, and PT-broken state if it does not. And what I mean by that is that, if you use the PT operator on that particular state, it is going to, respect the symmetry, basically. Okay, so another fact that that is the minimum uncertainty states, if we're looking at these, we can know what those states will be, basically. So if we are looking at the observables A and B, the eigenstates of the operator A plus I lambda B, where lambda basically is the ratio of the fluctuations of A and B. It's going to be a number. So A plus I lambda B is that one operator whose eigenstates can be the minimum uncertainty states. So I'm mentioning this because I will be talking a little bit about the minimum uncertainty states. But the question arises with this because MUS are very important. Minimum uncertainty states are very important because in a sense, they mark the boundary for the violation of the uncertainty relation. Sometimes we may wonder, if I have a minimum uncertainty state, that means a state that is saturating the uncertainty relation, whether it is PT symmetric or PT broken. Okay, so that's a genuine question that we do also ask. By the way, so now getting back to our 2x2 system, we can construct the G metric for us in the PT symmetric phase in this way, and in the PT broken phase in this way. In the PT broken phase, it happens to be time dependent, but we deal with t is equal to 0 here. So these are the simple G matrices that we do have. And now we get to ask the question. Let's say the simplest things that we can think of in the 2x2 system is sigma x and sigma z. Okay, so let's say we ask the question, are sigma x, sigma z good observables? And when we say this, our Hamiltonian is non-Hermitian PT-symmetric Hamiltonian, and we are looking at the state, which is the generic superposition of the eigenstates of the Hamiltonian. And these are the observables that, and also we are in the framework of G inner product. Okay, and now G-metric inner product. And now we ask this question, and the answer is, okay, so the answer can be, there can be two answers. So if you have the Dirac inner product, then the answer will be different. And if you are using the G inner product, then the answer will be different, definitely. And in this case, we answer that if we do have the Dirac inner product, then there is no violation of uncertainty relation, and sigma x, sigma z are good observables, okay? And this is very much anticipated because it does not matter what state do you choose. Even though our state is a superposition of the eigenstates of the non-Hermitian Hamiltonian, it is, as long as you are in the Dirac inner product, it should, the uncertainty relation should be satisfied for any two incompatible observables, okay, for any quantum state. So that's what happens. It's not very surprising. And as we can see here, now again, this eta is basically the ratio of the left-hand side of and right-hand side of the uncertainty relation. And we see that there is no violation of uncertainty relation seen here, okay? So much expected in any of the phase. This is for the PT symmetric phase, and this is for the PT broken phase. So different values of gamma, less than 1 and greater than 1. Right. So far, so good. Now we get into the G inner product, let's say, and we ask the same question. Are sigma x and sigma z good observables? And the answer is no, not within the G metric inner product. The uncertainty relation is violated. We can see it here, and we can see the violations in the PT symmetric and PT broken, both the phases. What is happening here? Why these are so? So if you remember, I talked about good observables. And as it turns out that sigma x and sigma z are basically not the good observables when you look at the geometric inner product, okay? Which means that commutation relation that involves G basically, okay? So in here, we can already see that sigma x and sigma z are not good observables, but in fact, sigma y would be a good observable. So if you take your G and you take your sigma y to be the observable, you can see that the commutation relation that I showed you earlier as a condition of good observable will be satisfied. So we know that sigma y is a good observable. Now, as it turns out, we can basically construct these good observables in both PT-symmetric as well as PT broken phase. And they look something like this, okay, where x and y will be the real numbers. So as long as you can write your observables in this form, you can have these good observables that will always satisfy the uncertainty relation within this new geometric inner product framework, okay? So now, obviously, one asks the question, is our Hamiltonian a good observable? And the answer is yes, it is a good observable in the PT-symmetric phase. In fact, H gamma, so I already mentioned to you that sigma y satisfies the condition of good observable. And we see that H gamma is a good observable in the PT-symmetric phase, but not in the PT broken phase, okay? So in fact, we can see that H gamma and sigma y will make for two incompatible good observables, okay? But in the PT-symmetric phase, but in the PT broken phase, what happens is that H1 over gamma and sigma y will make for this set of incompatible good observables. So, for example, if you wanted to check the uncertainty relation in the PT-symmetric phase, you will take H gamma and sigma y and you will see no violation. And in the PT broken phase, you take H1 over gamma and sigma y, and there will be no violation. But if you took H and sigma y in the broken phase, definitely there would be a violation of uncertainty relation. So this is basically the idea. The uncertainty relation holds good as long as one chooses the good observable, no matter which phase you are in, okay? So now this is what we show. As I mentioned in the last slide, this is just a pictorial representation of the same. So this first picture here is the PT symmetric phase. The second one here is the PT broken phase. As you can see that in the first picture, we are taking H gamma and sigma y. Those two are good observables. They satisfy our good observable commutation relation. And so there is no violation of the uncertainty relation seen. And also in the PT broken phase, we take H1 over gamma and sigma y, and no violation is basically seen for the uncertainty relations. And this is eta G, which means that we are in the geometric inner product framework, obviously. So this was for 2x2 systems. And now if you want to generalize this whole thing for an arbitrary dimensional system, an n cross n system, in fact, the recipe to derive the condition for good observable can simply be extended. If you wanted to derive the uncertainty relation using the geometric inner product, that can also be done. So it's there in the appendix of the paper, the archive paper. You can also generalize it to n cross n system, which uses n cross n PT invariant Hamiltonian. Of course, the major challenge is to find incompatible good observables to construct the uncertainty relation under the G inner product formalism. So for 2x2, it was kind of easy. And you also see that we already have the H as good observable in the PT symmetric phase. And we could also see that H1 over gamma is the good observable in the PT broken phase. But that's not so easy to do for n cross n systems. However, we can see that one good observable that you can find in this n cross n system is the G itself. So the G acts as a good observable in this. The question remains, is Hamiltonian still a good observable in the PT symmetric phase? And the answer is yes. So how do we check that? For the n cross n systems. So we can take, let's say, for example, two different Hamiltonians, and the entries, the non-zero entries of these matrices HA and HB, let's say these are two Hamiltonians that we are looking at. The non-zero entries of the matrices are given in this fashion. You have to do a little math to construct these matrices, because these are written in the compact form, n being an even integer. Okay, so if you have this HA and HB, what we can see here is we can define an operator K in this fashion. And now you see that your H and G have a tilde on top of it. And those basically talk about, so if you have, so why we use the sign tilde? Because you can appropriately choose your HA, HB, and correspondingly choose your G as well. Okay, so once you have those, you can construct this operator K and have a new identifier kappa, which can be defined in this fashion. But the kappa is defined very carefully. It is defined in such a way that it uses the good observable condition. Okay, so for good observable, your kappa will basically be 0. Okay, and it will hold a non-zero value otherwise. So now, because we have our H and G encoded in here in the kappa, we can see that we can have kind of a comparison of this kappa, which will only be 0 for good observables, with the gamma that was our Hamiltonian parameter. Okay, that helped us see the transition from the PT-symmetric to the PT-broken phase. And what we see is that we had two Hamiltonians, HA and HB, for definite numbers of n, the size of the system. We check this and we see that, okay, so the one point that I would actually like to mention, that for these Hamiltonians, the EPs are already detected. This is done, this work is done by, I'm sorry, I haven't put the reference in here, but this was done by the rest two of the authors of this work, actually. And they have given the exceptional points for these two Hamiltonians, HA and HB. So we know basically that these exceptional points are, I should have mentioned them here. So for HA, for example, it is 1. And for HB, it is somewhere at 0.48, if I remember correctly. Okay, so these are the exceptional points, which means that that is our distinction point to differentiate between the PT-symmetric and PT-broken phase particularly. But now our kappa defined in this particular manner, which says that it will be 0 for good observables and non-zero for not good observables. We can see here that for this case of HA, typically, this red line and this black line. So we can see that your transition point gamma is equal to 1, which I already told you, basically tells you that your Hamiltonian H is a good observable in this particular region, because kappa takes the 0 value here, and it starts to become non-zero at this point, exactly at the EP. That means that our Hamiltonian is a good observable in this region, which is basically the PT-symmetric region. Similarly, for HB, you see that this is around 0.48 here, and that means that the good observable condition starts to get violated exactly at the exceptional point, which is 0.48. So kappa again starts to take non-zero value for this at this gamma is equal to 0.48. So we can say from this that for such systems, actually our Hamiltonian, being a good observable, can be used as a diagnostic tool to see this transition from the PT-symmetric phase to the PT-broken phase. Which is what I have typically written down here. So these are the values that I was talking about. Okay, so this is a very good use in such, non-Hermitian systems that follow PT symmetry, that you can basically use our good observable condition to see the transition and to see the exceptional point. Okay, so to summarize, I think I'm done with this. So to summarize, the first point that I would like to mention. Basically, in the result, what we did is we defined good observables for arbitrary n cross n non-Hermitian PT symmetric systems. So we gave a condition that, of course, within the G inner product framework for non-Hermitian PT symmetric systems, that tells us if an observable is a good observable or not, in order to look at the uncertainty relation. Okay. The good observable can be Hermitian or non-Hermitian both. Now we wrote down, or we constructed the uncertainty relations for such systems within this inner product formalism. And that looks simple. And using these good observable conditions, we can always check whether the uncertainty relation gets satisfied or not for a particular set of incompatible good observables. Then the other thing is we looked at our Hamiltonian. It is a good observable in the PT symmetric phase always, but not in the PT broken phase. For 2 cross 2 systems, we have a neater description, because we also know what is a good observable in the PT broken phase. It is H1 over gamma. But for n cross n system, we still the good observable condition still holds. We know that our Hamiltonian is a good observable in the PT symmetric phase, but it remains to be a challenge to construct a good observable in the PT broken phase as neatly as in the 2 cross 2 systems. Okay, so this is basically the summary of the work. And if you want to take a look at the schematic picture that describes everything, then this is it. This is our good observable condition. In this region, the orange or red region, the good observable condition is not followed. In the blue region, it is followed. And our Hermitian or usual quantum mechanics will remain in here at the center, where your G will take the value identity. And this gamma basically is the Hamiltonian parameter. So you see that when gamma is equal to gamma EP, which is your exceptional point. So for that particular value, those points will lie here at the border. And if, right. Yes. So at the center, of course, you will have your gamma 0, and that will come to your usual quantum mechanics, in the sense that if you're looking at the inner product. So this is the depiction of the good observable condition on our Hamiltonian precisely. So that's all I had to say, and I'm ready to take questions if any.
Hello, Namrata. This is Professor Prince from NIT Srinagar.
Hi, how are you?
How are you?
Yeah, thank you for
very nice talk. So thanks for this wonderful introduction. So can you tell me how you fix this gamma? I mean, I don't get this point. And how do you know what values of gamma you have to choose? Or it is arbitrary, you have to take a range of values to fix gamma?
Yes, so it has to be a range of values. And for example, for 2 cross 2 systems, the Hamiltonian that I used, we know that the transition point is at gamma is equal to 1, and gamma less than 1 is this, gamma greater than 1 is PT broken phase.
Right. Now, is there, for example, a specific value of gamma that I have to choose, say, for PT symmetric or PT broken?
Yes, absolutely. So, for example, if I remember correctly, for our pictures in the PT symmetric phase, we are using something like 0.5 or 0.6, and in the broken phase, it is, Sorry, I should have mentioned.
Very nice talk.
Thank you.
Please mail me the PDF of it.
Sure.
Thank you.
Yeah, hi Namrata. Thank you so much for the nice talk, and the floor is open for questions. If I think there was a question in the chat by Lakshmi Prasad Naik. Can you just go ahead and ask it? Lakshmi Prasad, are you online?
Okay, so can I read the question?
Yeah. If you can read the question, yeah, just go ahead, please.
Yes, so he says, can we say PT-symmetric case to satisfy hermiticity partially because the spectrum is real? Can you briefly say what is the reason for introducing G formalism? I couldn't get the point. Okay, so the answer to the first part of the question is yes. So in the PT-symmetric phase of, even though you are having this non-Hermitian Hamiltonian, in the PT-symmetric phase, everything should basically work like the usual quantum mechanics should be reproduced, so to say. And can you briefly say what is the reason for introducing G? So if you are having the non-Hermitian Hamiltonian, of course, you will need to define the inner product that satisfy, let's say, the bi-orthogonality in order to have the quantum mechanics framework. So that is why a new inner product is needed. And there are several candidates for this, and G metric inner product is probably the best one in the sense that it also applies open phase.
Yeah.
Okay, the next question is by Nachiket.
No, I think there are no questions related to the talk. So does anyone else have a question? Could you please come forward and just ask? Okay, so Namrata, I had two questions. So the first one was, maybe you've answered this somewhere in the talk. Maybe I missed it. So, how do the exceptional points actually affect the uncertainty principle?
Okay, that's a very good question, so to say. So just let me go back. So when you say, what do you exactly mean when you say, how do they affect the uncertainty principle? Are you into the physical interpretation or?
Yeah, so what I mean is typically like, so exceptional points also have a connection to lasing systems where you have loss and gain, and there is an exchange of loss and gain, and you come very close to the exceptional points where you get some interesting topological features as such. I was just wondering, even if you're thinking of, if you are calculating such uncertainty principles and you're approaching an exceptional point where the eigenvectors become equal, so what would suddenly happen as you really come close to these exceptional points? Like, okay, so numerically, I know, like, if you try to come close to an exceptional point, even numerical errors become extremely large. So analyzing it becomes very difficult. So
Absolutely.
Yeah. So do you have anything, Eddie?
To be honest, no. To be honest, no. I haven't thought about it.
Yeah. So another thing is, like, PT systems are also connected to open quantum systems.
Right.
So is there any way you can connect the uncertainty between closed and quantum? Like, is there any literature on that, or?
Not that I'm aware of. You're asking really good questions. So no,
okay.
This is actually intriguing because I would probably go back and take a look. So I'm not aware of any such literature.
Yeah, I was just curious about this because this is a very interesting, because it allows you to check the uncertainty in both the cases. So I'll also go back and read it. But thank you so much for this very interesting talk.
We can talk
I'm
about
sure
it
it
at
is.
some point and try to work together.
Yeah. Thank you once more on behalf of, I think, the organizers as well as all the students and researchers who are attending this talk. Thanks, Namrata. And